Good morning, good afternoon, and good evening to all. I'm Adam Englander. I've been a member of the Palettes team since about 2019, and I'm here to present Quart in action, async APIs for model front ends. In this presentation, I'll be describing the creation of an API interface to a large language model with Quart. The premise behind this presentation comes from a proof of concept I completed at my company to host and sell access to large language models via an API. So if you're unfamiliar with Quart, Quart is like Flask, but from an asynchronous alternate universe. It has a nearly identical API and utilizes many of the same libraries. Hopefully, one day, it will be merged into Flask, and they will be one project. That work's been ongoing now for at least 3 years. So large language models, you may be more used to them being called LLMs. These are models of which most non-data scientists are aware. They include ChatGPT, Midjourney, they're probably the most well-known. Google Gemini's made a lot of splash recently. DALL-E 2, Llama 2, Stable Diffusion, you may also know. What you may not know, though, is some of these are open access, and you can run them with little to no licensing restrictions. For this presentation, we'll use none of those, mostly because they are way too large to run on an ordinary computer. We're using GPT-2 because it's popular, open source, generates novel text output from text input, making it easy to demo, and it's small enough to run on most PCs. Receive requests that are fairly simple. What do you want to ask the large language model to complete? And it will respond with a barely related completion answer. Again, it's not a very good completion result. It does, however, run on a laptop. Models that produce good completion results do not run on a laptop. GPT-2 will, which is the most important part. And as you can see, it's not a super useful answer. So why Quart? Why not Flask? And the basic reason for that is models. Models, and especially LLMs, have special resource considerations. LLMs are resource hungry. Most will require all of the resources of a single server for one inquiry. Having two model inquiries competing for the same resources can be disastrous on all but extremely expensive and difficult to acquire hardware. So we need to avoid running more than one model inquiry at a time. This is in stark contrast with traditional web apps, which consume a tiny bit of CPU and a lot of I/O as they talk to databases and other services via the network. That's why your web application can service numerous simultaneous requests on a small amount of shared and inexpensive hardware. The limited need for CPU resources allow Quart to share them successfully with an LLM. To limit the resources consumed by LLM inquiries, we need to process them serially. This will allow us to process each request while limiting the resource utilization to acceptable levels. So now that we have a base understanding of the problem and a high-level solution, let's design it. ASGI apps, asynchronous server gateway interface apps, like Quart, allow us to simplify the architecture drastically, as they can process multiple HTTP requests simultaneously with a single worker. This provides the capability to completely enclose the LLM inquiry within our Quart app, which looks something like this. Requests are sent to the only running ASGI worker to be routed to the view function, which sends an inquiry to the LLM. That seems simple enough, but there probably wouldn't be a talk about this conference, if this was just that easy. There's an inherent flaw with the design. LLM calls are not async, and therefore they block, and block for a very long time. The libraries for interacting with local models execute an unknown mix of Python and C code that will block our ASGI worker from processing any more incoming requests before the LLM query has it completed. And completion takes a long time. On my laptop, this demo takes 6 seconds for one request. To alleviate this, we'll move all processing for the model into a separate process. which allows for processing HTTP requests and model requests in distinct processes, which will not block each other. We'll use queues to communicate back and forth between the processes for two reasons. First, we want to process one model inquiry at a time. Second, queues are easier to use than pipes in Python. This is the final solution we'll end up building. So now that we know what we're building, why we're building it, and what we're using, let's start the basics. And to let you know, the remaining portion of this presentation includes code samples which should be readable. I'll be moving through them quickly. If you have trouble grasping what's happening in real time, it'll be available in a code repository which is highly commented with explanations that are removed in the slides for readability. A link to that repository will come at the end. So first we'll build a base Quart and Quart schema app to start. We have a very basic project with all Python logic in app.py and dependencies and requirements.txt. For the base API, we only need to install the Quart and Quart schema dependencies. The app.py, which you're not expected to be able to read right now, has a basic hello world type functionality. The classes and functions to create the base Quart app and Quart schema are imported. The Quart app with Quart schema extensions, with the Quart schema extension is installed. A pydantic model for the request is defined and the response. And we define a single view function for the API path. It returns a simple result based on the request input. This base app allows for validation that the Quart portion is working before moving on to the model inquiry process, just to make sure that you have a working point and you know how you broke it moving forward. So let's get right to adding in model inquiry processing. So we start by adding the Hugging Face Transformers library. As you'll see in the code, it's dead simple to implement. We're including PyTorch rather than TensorFlow or JAX because PyTorch has a greater coverage for model support. We add some configuration related to the model. We define that we're using GPT-2 as the model. The model value is either a model identifier for the Hugging Face repository or the location of model files. We're just using the model identifier. We set where we will store the model file. We're pre-downloading it and need a place to store it. We set the max token generation length. If you have a resource problem making the example code work, you can reduce that value until it works. The more tokens it needs to generate, the more resources it utilizes. So now let's get down to processing. So we have our original diagram for the design, and we'll break it down just into the parts that we're building, which include the view, the request and response repositories or queues, the model request process, and the LLM itself. So from this we identified the flow. Some pieces were necessary to add to make it work properly. So we've added new elements to the diagram. We now have both a response processor and a future store. They're both part of the Quart app. The response processor gets the responses from the response queue, such that the view function can continue processing with the response. The future store is a crucial part of that process. So let's see how that all works. So first we are going to design our queues and store. We use multi-processing queues, as the queues will be accessed by multiple processes. The request future map is the future store from the diagram. It's a simple implementation for a crucial role. Now that we have those, let's focus on the view. The view takes incoming API requests and puts them into the request queue, and then stores a future in the future store and waits for it to be fulfilled. So let's take a closer look at each of the sections. So we've made no changes to the definition of the view function. Itself, we're just adding LLM inquiry logic. We add logic to create a future from the async IO loop, generate a unique identifier for the request, and place the future identified by the request ID in the request future map. Then we put the request and its ID into the request queue. Notice how block is false. Multi-processing queues are blocking for async functions, so we tell it not to block. And catch the exception when the queue is full. will retry after relinquishing processing with a sleep 0 until we successfully put the item in the queue. The queue being full is unlikely to occur in this implementation, but it's good form to assume it might. Now the request is in the queue, we wait for the future to be fulfilled. Once fulfilled, we'll return the response. Spoiler alert, we'll be waiting until the response processor fulfills the future. So the next logic to build is the request processor. The request processor pulls requests from the request queue, generates the response from the model, and places the response in the response queue. The entire request processor is 13 Python statements, with only 2 of them required for interacting with the model. As I said earlier, the transformer library makes it incredibly simple to interact with the model. Let's look closer at the selections of code in the request processor. Well, the processor itself is just a function that will be run in a separate process. The function will take a model, request queue, and a response queue. It'll create a pipeline for text generation against the provided model, and will also quiet down the logs to remove unnecessary noise. We then run a loop forever to get a request and its ID from the queue, process the request via our pipeline, and place the response or exception incurred with the request ID in the response queue. As this code is not async, we're not worried about blocking on the get and put calls on the queues. Now we need to build a response processor. We've got something to process the requests, to stick them in the response queue. Now we have to build something to take the responses from the response queue and then fulfill the promise. It's another small piece of logic, and let's look at it more closely. So we're defining for the response processor an async function, as the function will be run as an async task in order to have access to the future store housed in the same process as the view function. It will be supplied the response queue and the future store. When called, it loops forever, pulling responses and request IDs from the queue, acquiring their corresponding future, and fulfilling it as either an exception or as a result based on the response. As this function is async, we also use the non-blocking method for getting items from the multiprocessing queue. There's no break in the loop when successful, as it's a continuous loop to just get items from the queue. And so it will always loop until it gets the response and then process, and then continue on processing forever. So that was the entire process. It's not a lot of code, but the concepts are fairly advanced. So now that we have the logic built, we need to add the bootstrap and teardown logic for the request processor to process their tasks and services. So fortunately, it's fairly simple. We define an async generator function and decorate it with while serving from the Quart app, which is a Quart application lifecycle decorator. An optional bit of logic that we're adding is downloading the model files explicitly. This alleviates long response times for the first request, as the transformers library lazy loads the model, which can be 500 megabits for GPT-2, or megabytes, sorry, to multiple gigabytes for a model like Llama 2. If you have limited space and can't spare the extra 500 megabytes, simply comment out these 2 lines and be ready for a long request time for the request made shortly after the application starts. So next, we need to start the request processor. We use the multiprocessing library, to start the model request processor as a separate process. Then we'll start the response processor as an async I/O task. And then we'll yield to allow Quart to process the web requests. This is an async generator function, so that you can, there are start and stop, but it's a lot cleaner to use the async generator for while serving. Once the requests are done processing, we stop the response processor task. And then terminate the request processor task. That's it. That's all the code necessary to host a model as an API with Quart. It's a lot of extra work around. So next, let's put in some thoughts about hosting. So now that you have this application, you'll need to host your LLM API. LLMs are still relatively new. The majority of my strategies for hosting web applications do not apply to model APIs. Docker and Docker orchestration applications like Kubernetes are not designed for LLM model hosting. The metamorphosis from LLOps to MLOps to LLMOps, which is machine learning ops to large language model ops, is slow going. Hosting yourself is ridiculously expensive, as the hardware is nearly impossible to acquire, and if you can't acquire it, it is, if you think of the standard price for a production grade server, you're going to add at least another $10,000 per server for GPUs. There are options from Amazon, Google, Microsoft, Hugging Face, but they definitely create vendor lock-in. They also have strict limitations on the accessibility and availability of resources. If you can get resources, you may not be able to get enough resources to do what you want to do. So at this point, the only thing I can tell you is if you want to do something like this, find someone that will, whichever platform works best for you, and utilize that, because you don't have a ton of options. There may be more in the future, but it is what it is today. So wrapping up, although this is likely more of a thought exercise for most, I hope this presentation gave you some ideas of how Quart might help you solve some difficult problems. It certainly did for me. And as promised, here are the resources. There's the example code, which contains all the code plus a bit more. Again, it's highly, highly commented to help you understand what's going on at each phase. Quart and Quart schema, the transformers library from Hugging Face, and the GPT-2 model, if you'd like to know more about that. And thank you for the presentation.